Hello everybody, my name is Nicholas LaChapelle and I just cooked 2 pizzas and unfortunately none of them turned out quite right. One of them over here is completely burnt, inedible, and the other one over here has severely undercooked. So you might be wondering, aside from the fact that I can't, cook a frozen pizza, well, why did this happen? Well, simply put, when working with temperature, systems tend to behave in a nonlinear way. When you apply heat to a system, there's a phenomenon called thermal lag or temperature delay. What this means is that things take time to get hot, and even after you stop applying heat, the system can stay hot or even continue to get hotter. And that's not even taking into account that different materials heat up at different rates and don't always distribute heat evenly. Because of these nonlinear characteristics, traditional controllers, such as PID controllers, are often not the best at predicting the systems, can often overshoot or undershoot, which would basically kill my pizza. That's where fuzzy logic controllers come into play, okay? These controllers are perfect for temperature control as they treat their inputs as kind of like degrees of truth and then vary their output proportionally to that truth. Versus, let's say, a binary system which treats the 1 as the true and 0 as the false. For example, let's say if I had a temperature system that wanted to keep a temperature at 200 degrees. If my system at that time had a temperature of 205 degrees, the fuzzy logic controller would treat the input as like a mildly high input, right? And would vary its output proportionally. But let's say if my system was at 250 degrees, the fuzzy logic controller would detect that input as being way too large and then scale down the output much more to accommodate for that. Aside from making pizza, fuzzy logic controllers are extremely important in industrial settings. For example, in the plastic injection molding industry, where the majority of your plastics are fabricated, temperature control systems are monitoring the temperature is extremely important to make a good product. Which is why for our project, we decided to study these claims of fuzzy logic controllers and compare them for an injection mold machine versus a traditional PID controller. Now, we started with the basic temperature control model for an injection molding machine, where in this equation, K corresponds to the static gain, T is the time constant, and tau is the load delay time, which you may have noticed is kind of what is responsible for the thermal lag. Without a controller, we see here that the system's response is slow and really never quite reaches the desired temperature. When we add a PID controller, we do get a faster response, but it comes with a significant overshoot and actually fails to settle at the target temperature. Instead, it kind of just drops slowly and will eventually reach it, but not quite. Too slow. Now, after designing the membership functions and tuning the fuzzy logic controller, which took way too much time, we were able to get the best of both worlds. A smooth response with an extremely low overshoot, and it kind of oscillates accurately within the exact desired range. Now, through this project, we demonstrated that fuzzy logic controllers provide pretty much a better solution to controlling nonlinear systems, for example, temperature systems, and especially in injection molding. The results really speak to themselves when we obtained a lower overshoot, a smoother response, and constant stability. So while I might still burn my pizzas at home, at least I know how to control an industrial heater.